All right, so it's recording now. The red light is on my. So there's not a whole lot of slides today. I think basically this is going to be another one where the lab is longer than the lecture. So we're going to implement some of the ideas that we talk about. And since they're brand new ideas, I'm going to show you how to do it in Model Builder. So we'll do that when we get to it. Kind of create a recipe to start with too. I guess we don't need to enable editing. And who down on the coast was in Vandana's 417 class? Anybody? Okay, good. So it seems like up here, I was told, Corey, you were in 417. Yeah. And Elado was in 417, and you guys were both in 417 too, right? So I was told that last week's interpolation stuff was a little bit of a duplication. So Vandana, she's gone, so I can say she screwed up and she's not around to defend herself. But we sat down when we created all these new courses. Interpolation was supposed to be in this class in 418. I mean, there are ways to say that it's not strictly a raster issue, but anyway, we've both been teaching this class, and we so anyhow, there's some repeating, but this one I already checked with Elada to make sure. This one's not a duplicate. Okay. All right, so today we're going to talk about temporal modeling, and really we're going to carry that into next week when we talk about something called cellular automata. There's a few other names for it. We'll talk about that next week. So this is the beginning of temporal modeling. We have another week on it when we talk about cellular automata. So today we're going to talk about temporal modeling, and specifically one type of temporal modeling, and that is diffusion modeling. We're going to model in raster, GIS, the process of something spreading through diffusion. So we're going to have to define diffusion, and we're going to talk about what that means. So the first thing is that temporal modeling is really related to capability suitability modeling. In fact, it's kind of like capability suitability modeling, but we introduce another dimension, and that is time. So the capability suitability map is constantly changing through time, and that's causing the diffusion rate to change and to update. So capability suitability modeling, as you remember, is what will be the spatial extent of some phenomenon that can happen. So that's one way to phrase the question. Where is something okay to grow? Where is something okay to exist? How well can it exist? Those are problems that fall into this category. When we add the temporal aspect, we're updating the question to answer when will that phenomenon reach a certain spatial location. So a diffusion model is used to address questions concerning the paths the phenomenon could travel to locations and when it would arrive. So another thing that is assumed with a diffusion model is that we assume spatial contiguity is required for diffusion to occur. So this type of thing models phenomena that spread through spatial contact, like the way plants grow. Kind of the way diseases spread too, but diseases sometimes, well, they always spread through contact, but sometimes that contact, gets taken in an airplane more often these days, spreading from person to person. So we could include that. That would involve a little bit more complex model, but it's still essentially a diffusion model. So the diffusion model is used to answer if and when questions. If it's going to get to a certain place and when it's going to get to a certain place. So modeling a fire spreading, it would also be another diffusion model. We're going to talk about the next one. We're going to model that as an agent-based fire, or a cellular automata agent-based. I didn't know what to call the lecture next week, but it's both of those. Really, when we're dealing with raster, it falls a little bit more into the cellular category. Okay, so here are some phenomena that diffuse disease, such as West Nile virus. Infestations, we know what kudzu is. We don't have as much kudzu down here in South Mississippi, but we do have it in Mississippi. It's like invasive ivy stuff that came over from Japan. It didn't just come over here. They actually planted it to shore up road cuts, but it ended up growing everywhere. Fire ants were more of a mistake. They came through. This is the map of fire ant diffusion. They actually came in through some of our ports on fruits. As fruits were imported from South America. So now you have fire ants. They diffuse. We don't have fire ants everywhere. So we want to come up with a model to explain where fire ants would occur, or where kudzu would occur. That's what we're going to talk about today, and when they would get to certain points. So diffusion can be static, meaning that the factors that inhibit growth remain constant, or like with plants, most often with plants, especially like in the northern hemisphere here, or the southern hemisphere, where we have seasons, they can be dynamic, meaning the factors that affect growth change over time. So they change. One thing I wanted to mention, if I go back to this one, forgot to mention it, is that really we assume that the rate of diffusion is related to the inverse of the distance. In other words, it'll take longer to diffuse to a place that's further away than it will close by. And that's going to be a key here in a second. So there's some important things to consider. One is the origin. Where did it start? Because that's important. When did it start? So you've got that on the map here with the fire ants. Got that on the map when it started. And then the next thing are the factors. The factors, just like with capability suitability modeling, the factors tell us whether or not a certain cell, so it's a cell-by-cell basis, is even suitable for diffusion. Can it exist there? So we need to identify what the factors are. Sometimes the factors can be, like with plants, it would be, does it get sufficient temperature? Does it get sufficient precipitation? And does the amount of precipitation and temperature affect how well it can grow? There can also be barriers to diffusion. Some can be permeable, some can be impermeable. Obviously, most plants that grow on land can't also grow in water. So water would present a barrier to diffusion. Things like that. So, and then finally, the temporal nature of factors. So The lab today will cover mostly this first one, expansion diffusion. Spreads from one region to another and remains in the originating region. Relocation diffusion, which I think is better modeled when we talk about next week, spreading from one region to another where the item diffuses and it leaves the original location. Most of the things we talked about with plants, animals, and diseases fit better into that expansion diffusion category. All right, so what we're going to talk about today, diffusion modeling, really builds on two concepts. We talked about capability suitability modeling already. The other one is cost distance modeling. The reason we're going to use cost distance modeling rather than just distance, we could say something is just spreading a certain distance, but really, in order to throw in the fact that things can grow differently based on different conditions, we need to use cost distance modeling. So this rate surface is created in the same manner as the friction surface. So the rate at which things can spread through a particular cell becomes the same as the friction surface. The friction surface, I remember we talked about cost distance modeling, was how long it would take a particular thing to travel through a cell, whatever we're talking about. If we're going to build a new road, it might be the cost associated with buying the land and things like that. Well, here, the rate, it has to be time. The cost has to be time. The time it's going to take to traverse through that cell. So it's easier to kind of think about, instead of thinking about it in time, it's easier to think about how quickly it's spreading. So usually we get it in that, we do the capability suitability model to arrive at a rate. So the capability suitability model, however that model is set up, will have as its output a raster grid cell. A raster grid where the cells represent how fast that this thing that we're trying to model will move through that cell. So one example of a rate is miles per hour, right? But we don't usually measure lots of things that diffuse. We don't see kudzu growing in miles per hour, right? Or even diseases spreading in miles per hour, or fire ants. That'd be scary, even if they were fire ants spreading at 1 mile per hour. That'd be scary. So we usually measure things at different rates, but we express the movement rate in distance per unit time, just like miles per hour is a rate. But typically here, we're saying that 100 meters per day is the rate at which it would spread in this example. That's still pretty fast for like a plant. But in any case, in this example, just so that it's an easy number for people to think about, we've got 100 meters per day in a forest. On bare land, it can travel faster, whatever this is. It can travel faster, 200 meters per day on barren land. It can't travel through lakes, so it just doesn't travel through lakes, so that we would code those no data. All right? So the movement rate that is always in distance per unit time, it has to get transferred into time, okay? Time per unit distance. And I said, a few minutes ago, I said if this was just Euclidean distance, it'd be growing at the inverse distance. And so this what did I do wrong? Okay, there it goes. And so in order to get time per unit distance, to get something that's a friction surface that we can use with the cost distance algorithm, we just go 1 over the time per unit distance. So that becomes the friction surface. So divide everything by 1. So now we have 0.01, and then whatever our time is, in this case it's days, it takes 0.01 days per, in this case, the distance is meters, per meter to get through that cell, okay? And you can see in the 200 we get a different number. In the 200 cells, like this one, 200. And it's just simply 1 over this grid. You can imagine this is a whole grid. This is just one row in the grid. This is another row in the grid. Finally, we put that through the cost function, and the result, when we put it through the cost function, we need a source. So we need to determine what the source is. In this case, it's just this cell right here, this first cell. We put it through the cost function, and when we do that, the resulting surface is in units of travel time, in other words, days. So the way that we read this is, since this is the source, it will be here in 0 days. It's already here. It'll be 10 days before it gets to the center of this cell. It'll be 17.5 days before it's in the center of this cell. That number, I don't know why that number is blacked out, but it would be another, 20-something days if we calculated that out. Then 30 days to get there, 40 days to get there, 50 days to get there. That one's blacked out as well, not for any good reason. Then it would not reach this area, and by definition it actually wouldn't reach this area either unless this grid was filled out and there was another way to get around these lakes. All right, so in order to implement this as a model, it's best to kind of think about it as a flow diagram like we have with other models in the past. So this portion of the model here, so the part that I'm kind of circling right there is the part that's basically a capability well, not all of this, sorry, just this part right here. This part is the part that's kind of like a capability suitability model. So we get our factors that are influencing diffusion, and we reclassify them to create a movement rate. And that movement rate is then used to get a distance per unit time. And then we take the distance per unit time, we do 1 divided by that, and we get the time per unit distance. This part of the model here, right there, is the is cost distance. Okay, and then once we do the cost distance function, what's the result? This map right here. It's now in whatever time units we've been using. Okay. Our next job is to establish what the time step of our model will be, because we're going to run the model over and over and over again, right? So if the time step of our model is every 30 days, let's say it's a month, how far, let's say it's 31 days, just so that the math will work on this one. How far did it get? If this represents the time it took to travel from the origin, how far did it get? Did it get to this cell? If it's 31 days, did it get to that cell? What's that value? Yeah, it got to that cell. Did it get to this cell right here? This one? Yeah. Well, this one should be 20-something. Got to that cell. Did it get to this cell? Yeah. Did it get to this cell? No. So we're going to make a cutoff there, and we're actually going to use a conditional function to say, now it started out in this cell, and after one time step, it's now in all of these cells. Then we could run this time rate thing again. And if we just ran the time rate thing again, this cell would get a value of 10 days that it would take to get to this cell, because this is now the source. So it'd take 10 days to get to this cell, 10 days to get to this cell, so many to get to this cell, and so on. Okay? So then we would do that again and say, okay, well, it could get all the way to here after two 31-day periods, which are months. We could decide that our time step was going to be 1 day. If our time step was going to be 1 day, where would the line be drawn? After the first cell. Okay? Now that's a problem. Because if the line got drawn here between the first two cells, in the next time step, where is it going to be? It's still only going to be in that first cell. It didn't grow out of the first cell. So when you're doing this type of modeling, you need to make sure that you establish a time step that gives it time to grow out of at least one cell. Or you have another option, and that is to get better data, more precise data that's smaller, so that it'll actually show it growing out of one cell. Because in reality, it's growing a little bit, but just not growing outside of that cell. So if you get smaller cells, you could have it grow, and then it would show up on the map. All right. So each time you have another time step, you use your new origin, and you use that as input into your cost distance. So you have a different source. Optionally, you can also change the factors every time step, if that needs to happen. So if you're using precipitation and temperature to model growth, which we're going to do in the lab, then you can change precipitation and precip every time step, as well as changing the origin. So this is a model that you have to build. You have to determine what the diffusion is going to be. Okay, this is just raster algebra. This is cost distance, and this is basically a reclassification or a conditional operation to create your new origin. Okay. This right here, this feedback, is really the only unknown. How do we do that? Well, that's one of the things we're going to talk about when we do the lab. So as I already mentioned this, your cell size and your time step are really important. You can't choose a cell size. Well, let's phrase it this way. You can't choose a time step in which your phenomenon will not spread outside of a cell. Because if it won't spread outside of one cell, your time step is too precise. It needs to spread outside of at least one cell in order for you to model the growth. So you have the choice to either make your cells smaller or your time step longer. You can model it on a yearly basis or a monthly basis or daily basis. So those are smaller time steps. Or you could model it on 5 meter data, 30 meter data, 100 meter data, 1,000 meter data. Those are cell size changes. Okay? Really, they're both measures of resolution. So what you're doing is you can't. They're related. You can't have really precise time steps and really precise, and not precise cell sizes, or vice versa. Remember, the time step must be small enough that the phenomenon can move at least one cell during the time step. Okay, that's important. All right, so that's all the slides. Took us a whole half hour to do that. But let's look at the data for this lab and talk about what it's doing in relation to what we just talked about. And then part of the lecture is explaining how to do this time step loop before we get to the lab. So I'm gonna download the lab data. I'm going to put this, so there's a file geodatabase and there's a toolbox that I have. I'm going to put this in CSA I thought I had, no, it's under ctemp SA, isn't it? ctemp SA, and then I'm going to create a new folder called Lab 9. Call it temporal, I guess, too. Paste it in there. So make sure that you paste both the data, which will take a few more seconds than some data sets to copy. It's a lot of data. And the toolbox in there. I'm going to go ahead and add. I'm going to go ahead and add the toolbox into ArcGIS. So ctemp SA Lab 9. Oops. So I'm adding the toolbox in. I'm also going to add all of the data. That's in climate data. I'm going to add it all in. We'll talk about some of the questions that we'll have to answer later, but they're related to why we have the states on here. All right. So I want to explain the data a little bit, although I explained that in the lab. These are the average monthly precipitation and the average monthly temperature values. I probably should have added them in a better order than I did. I just kind of threw them in there haphazardly, didn't I? I could like sort them out by precip and temperature. The output here, we can throw that away. Don't need that. All right. So these are all the values. So what's on top? Temperature. Well, what do you suppose that means? Temperature underscore 12. What's that? Does it?
No, it's monthly.
It's December's, right? It's December's. It is in degrees times 10. So, and it's in Celsius. So it's 26.87, or is that's times 100, I guess. Temperature times 100. So 26.87 is the average, the highest average December temperature value. So that occurs somewhere down in South Florida. What is 26.87 degrees Celsius? It's pretty warm. Okay, we're not even in that range. 26. Let's see, in almost 80. So that's the average temperature somewhere down there in South Florida. I don't know exactly where it is. You know, even I grew up in a warm climate, but it's not quite that warm in Southern California. Let's see what it is. Right there. It looks like the average temperature is 19.17, which seems like it's in the 60s. That's probably reasonable temperature for December. pretty cool at night. All right. I do think it's the average daytime temperature, though. Okay, so we've got 12, 11, 10, 9, 8, 7, 6. So we've got all the average months of the year. And all the months and all their averages. Same with precipitation. We've got a precipitation value here. Let me turn off some of these. Oh, here's the first precipitation. So this is February precipitation in the United States. Is that what you'd expect? Look reasonable? Where's it raining the most, it looks like? Well, the southeast is raining a lot. Okay. There's also raining a fair bit in the mountains on the Pacific coast. And again, I grew up in Southern California, and when it does rain, the winter time is the time for it to rain. Okay? So growing up, looking at these mountains, these were the only times it was starting about April or May, it started getting brown. Okay. So that's precipitation. The reason that this data is included is that these data are going to be used to model the growth rate. And in the lab, I didn't specify what invasive species this was. Oh wait, I put the text of the lab separate this time. So you have to download that separate. There's 25 grids. One set of 12 grids is the average monthly temperature. They're in Celsius times 10. Two set of grids is the average precipitation values. They're in millimeters times 100. It's actually it's more efficient to store a number not as a data point, not as having a decimal point. So you see lots of times when people distribute data online, they'll take the decimal point out, but they'll compensate for that. Like if they just want you to have two decimal places, they'll multiply everything by 100 and convert it to integer. Because an integer grid takes less space to store on disk. Particularly when all the values you know are going to fall in some range. So there's never going to be a temperature value that goes beyond, in Celsius, goes beyond 30 or 40. That's going to be the highest that we get, particularly in the United States. So if we multiply it by 100, it's actually by 100, I guess. Yeah, it's by 100. But anyway, definitely by 100, because if it was just by 10, 267 degrees Celsius. It's like really high. So it's definitely by 100, but in any case, your biggest number is going to be 4,000, and that's like really, really high. So that's going to be a smaller. Every raster cell has to have the same amount of data stored in it. So if you have a raster cell that can hold a decimal place, your raster data set is like twice as big as one that's holding an integer value. Okay. So for the lab, we're going to execute temporal steps that will show the diffusion of the weed based on the following criteria. I just call it. It's not going to spread into areas that have an average temperature less than 21 degrees. It's just not going to spread there. That's what type of capability suitability? That's like a barrier to diffusion. Okay? Less than 21 degrees Celsius, it won't go there. Other than this, other than this constraint, weed is not affected by temperature. No weed. Weed makes it sound like it is marijuana. It's not marijuana. It's not an invasive species. Other than this. Exactly. So it's not affected by temperature. So the only thing that's affecting growth rate in in terms of temperature is it less than 21 degrees or more? Okay? The weed is very influenced by the amount of precipitation that it receives. It diffuses at a rate that's been determined to be 1 meter per day. That's a much more reasonable amount. I mean, it's still growing pretty quick, but for every 10 millimeters of precipitation. So every 10 meters of precipitation makes it grow a little bit faster. Okay? In our example, we're going to introduce the weed in June. So we're going to build a capability suitability model that will create the rate surface first. Then, once we do that, we're going to implement the time step approach. That part is the part that we need to do, or at least we need to discuss together, okay? Because that's all brand new kind of material. We're going to go through the first part, okay? But you should understand these concepts pretty well now, okay? What I did was I created a recipe for one time step that does one time step. That's what we're going to go through together. And then we're going to do the second part, the time step part of it. All right. And at the end, just for fun, these are the questions we're going to ask. So this is what we're going to do together. Part 2 of the lab will modify the model so that it does loops to a specific part. Part 3 of this lab will be to modify the model so that during each loop a table is created that displays the total affected area for each state. So that, well, think about that for a minute, okay? We want to create a table that is going to create the total affected area for each state each time through the loop. We're going to modify the model to do that. So what you need to do is think about what tool would do that. How would you do that? Think about states as something. So, yeah, okay. I didn't necessarily mean for you to answer it right now. That's great. I was saying, think about it. We'll come back to it. So that's right, though. Exactly. That's great that you came up with it so quick. So, yes. So each time through this loop, we're going to add a zonal statistics to this table, and it's going to tell us how many the areas of both categories. Then you could just create a new field and divide one category by the other, and we'd be all set, right? Okay. All right. So turn the model and a line chart showing the area affected over a 1-year period for North Carolina, South Carolina, Tennessee, and Virginia. Kind of like, if you were working for somebody that was interested in running this model, and they'd be like, what percentage of North Carolina will be affected in 1 year? Then you could refer to your table. Okay, back to ArcGIS. So here is the model that I just added, called the Temporal Modeling Lab Toolbox. So we're going to create one other. Toolbox later, but first, not toolbox, another model later. But first, we're going to discuss what this model is doing. You can lay it out however you want. I'm just going to keep it laid out like this. Just make it larger. Okay. So remember, our inputs are precipitation, temperature, and the source. Those are the 3 inputs, right? Precipitation, temperature, source. I chose this time not to do it as a raster calculator approach, but you could have done it that way. So I broke this out so that the conditional operator is done as a conditional operator. The division is done as the division, not as a, so like, that way everything appears in the model. It's just a different approach that I took last time. Okay, so first let's look at precipitation, because I said, how does the growth rate affected by precipitation? I want to start with temperature. How is the growth rate affected by temperature? That was the first criteria. Right. If it's less than 21 degrees Celsius, it can't grow. Right? If it's greater than 21 degrees Celsius, it's fine, it can grow. So that's why I have the conditional expression. If I open up this conditional expression, what do you expect to see? Yeah, both of you are right on there. So if the value is less than 2100, because remember it's multiplied by 100 as we really said, then the true raster is the value is going to be, we have to click on this to see what that value is going to be. The value is going to be 1. Okay? So the output there is going to be either 1s or 0s. The next thing that I did was I used the float tool. So that's the equivalent of saying float parentheses around the data set. The reason that I converted it to float was that if you don't do that, when you multiply an integer by a decimal, you'll always get an integer. So this multiplier up here has to take in 2 float values in order to produce a float value. And since the growth rate, we want it to include decimal places. That's why we have that. We have 1 here and 1 there. Okay. All right. So we're up to here. Let's go to precipitation now. Precipitation just said that we take the precipitation value, we divide it by a constant, which I gave in the lab. The reason why, which is 10. The reason why I did it like this is because I could make these parameters later on if I wanted to, and then the user could actually tweak them a bit and run the model over again. So right now I left these as constants. You can't change them, but if I right-clicked on it and said parameter, then it would put a little p here, and then later you could change it. Kind of like we did with the cost distance modeling lab earlier. So we divide that, we get the output. Why are we doing this other divide? Yeah, this is the divide by 1, exactly. So if I look in here, you're going to see this value is 1, and I divided by 1. So why didn't I divide this one by 1? It's kind of a trick question. This is producing the per unit time, okay? Okay, it's kind of a trick question. It really wouldn't matter if I divided by 1 here or here. Because this is multiplying by what? 1. So anything multiplied by 1 is 1. The more important thing is it's either multiplying by no data or 0, or what doesn't matter. It's the same effect. When you multiply anything by 0, what do you get? And you multiply anything by no data, you get. Right, okay. So this path right here, this path is multiplying by 1s or no data, by 0s or no data, or by 1s, which is keeping everything the same. So this was just a decision. Okay? I could put it here, I could put it here, because all this leg is doing is, it's not adding to the growth rate, it's not changing the growth rate. It's just basically a barrier or not a barrier. If the temperature was affecting the growth rate too, I would have to have this happen right here. It would have to do that to this, because I'd be combining these two growth rates somehow, and I would do the inverse at the end. Okay? I've done that before in this lab. I've said, okay, the growth rate is precipitation times this plus temperature times that. So I would do that and then multiply them together. Right? And this looks like stuff we've done before, we take the output, the inverse of the growth rate, so now it's in time. And in this case, I said in the lab, if we go back to here, the growth rate is it's in meters per day. So just because we shove them through these formulas doesn't mean any units change. The units stay the same. So now it's in meters per day. We flip it over, we do the 1 over. It's in days per meter. And so when we feed it through the cost distance, we get it out in days. So at the end, we're going to get this output distance is in days. It's called distance. The reason why it's called distance is because it's in the cost distance. But it's really output time. So it's time. And then this value, this conditional value here, why do I do this? Value less than 31. If I was really being slick, I could model. I could have a different number come in each month, but I'm just using 30. 30 is the cutoff because this is less than 31. So if it's less than 31, it gets cut off. So I'm overestimating a little bit in February, and I'm underestimating in what, January, March, all the months with 31. Okay. So that's this conditional operation. So that's one time through the loop. I get a new area out there. All right, we can go ahead and X this out. I don't know if I'm going to say yes. I don't think I saved anything though. Okay. So like the other models, it's important to run it by double clicking on it rather than try to run it in the model. Double click on it and fill in the values. So I'm going to fill out, when did we say it was starting? June? So June would be 6, right? So I'm going to go to temperature 6. Temperature 6, precip 6, precip 9, precip. I should have sorted everything, right? There it is, precip 6. And then I'm going to select as the source. I gave you all the source. You could change that if you wanted to. All right. Making sure I got enough space here. Okay. Then the new area is basically going to be the source after June. So I'm going to call that output. I'm going to go temp lab 9. I'm going to put it in the same folder. I'm going to call it output _ 6. And it stands for output of June output, where it got to in June. All right. So save that. Then finally, the last thing I need to do is make sure, because I'm doing things, the extent of the source is really, really small. Let's see if I can show it to you. Yeah, it's on. Turn all these guys off. Should work now. Okay, that's the extent of the source. You see that little orange dot right there at Cape Fear? That is the source. I don't know why I chose to send it into Cape Fear, but that's where it is, okay? So There it is. So because that's so small, if we didn't change the environments to be everything, the entire map, it would use the minimum extent is always used as the default. So let's change the processing extent to just change it to the temp. Any of these will do because they all have the exact same extent. But I'm just going to choose temp 6. Actually, I'm not going to go through the. Any of them will do. So you could literally change it to everything. I'm also going to change the cell size, which is 5,000 meters, by the way. And that's the only one. Those three are all the ones that you need to change. So extent, snap raster, and cell size. I'm going to say OK. And then I'm going to say OK. And then it's going to run, and the result, the output, is going to be a little bit bigger than this orange dot. And it's going to show where the weed got to. All right, there it is. That's the output for 6. Now, if we wanted to, we could go into geoprocessing, results, and rerun it again. Seven. And change this to 7. See that? Why did I just change all those to 7? Now I have to run it through double-clicking on the results. If you don't run it through double-clicking on results, you'll have to do all the environments over again. Okay? Yeah, go ahead. Just same as any of the other, literally any of the other grids. But the source. Any of the temperature or precipitation grids, they're all the same. They all have the same extent, corner, and cell size. So why did I change this to 7? Yeah, so now 7 is July. So now it's going to use July's precipitation, July's temperature, and it's going to output, at the end of July, it's going to output a value. So I'm going to say, OK, and I'm going to run it through again. And the end result, close this up, when it finishes, is going to be the next step. Output 7 is going to be the next step. All right, close that up, close this up. So see how I move 6 above 7. So 6 was the extent after June, and 7 is the extent after July. Now it looks kind of like it's just a concentric circle, but it's actually not. It's growing faster this direction than it is growing this direction. See how it's like on average it's only 2 cells this way? It's like 4 cells that way. Okay? Why? Why is it growing faster this way? Yeah, well, in this case, it's really just precipitation. But if I use temperature in the model, then it would be temperature and precipitation. So yeah, there's more precipitation up here, so it's growing faster. And, the same thing is going to happen over time. It's going to, as it gets to areas that have higher precipitation values for that month, it's going to grow faster into those areas. I don't have a precipitation value. Yeah, I do. Yep. So it's going to grow faster as it reaches faster precipitation values. All right. Okay. So So we could manually just keep going. We could keep this process up, right? Now you understand how it works. I've explained to you how the tool works. You could double click on this tool and rerun it and rerun it and rerun it. How many times would we have to run it for a year? 12, right? When we get to, so we run it 6, 7, 8, 9, 10, 11, 12. When we get to 13, what do we do? What's that? When we get to 13, what do we do? Start over, yeah, because it's yearly. So we're assuming that the growth rate will be based on historic data. Historic data. So that's just one of the assumptions of our model. I mean, if it ends up that we have a really dry January, then we're in trouble. Okay, we could do a stochastic approach where we have a probability of different rain values, and we could actually run the model like 1,000 times, and we could see, okay, well, it'll probably get to here, but we could see how saying, okay, if we run it 1,000 times, sometimes it's going to get to this, sometimes it's going to get to there. Once every 100 years, it'll get this far, but there could be times when on super dry times where it'll only get this far. Okay, we'll talk about that kind of thing in later models, but right now we're just saying on average this is how far it's going to get each year. Okay. If we wanted to do something like that stochastic approach, or even if we wanted to run this for, let's say, 5 years, you would all agree that doing what we just did would get really tedious, right? You get tedious to keep pressing this button and putting in the new values. You could do it pretty fast, but it would be nice if you could just enter all of the values that you wanted to, the start month, the end month, okay? And then you could just go and get a soda down at the end of the hall, put in your 50 cents, drink, and then come back, and it was all done, right? That'd be nice. So how do you actually automate that process of a feedback loop? So that's what we're going to get into for the lab. Speaking of that, I'm drinking a soda. I think I drank too much, so I'm gonna be right back. But what you need to do is create a new model, and then we'll talk about how we do this. Okay, if you're curious, I'm only going to be gone for about 5 minutes, maybe even shorter. If you're curious, what you should do is look up feedback and iteration in ArcGIS, and that's what we're going to do. We're going to do that. I'll show you how to do it. So you don't need to look it up if you don't want to, but I'll be right back.